Hello everyone, this is Mr. Lee. In this video, we are going to go over the kinematics equations. So our entire unit is named after kinematics, and kinematics is the study of motion. So in front of you, you should see the three kinematics equations, and these kinematic equations came straight from College Board's formula sheet, and the note here is actually from College Board itself. They say that the X subscript that you see before you right here, so these X subscripts, it indicates the X axis, but you can use these kinematic equations for both the X and the Y, and maybe even the Z axis. So whenever you see a tiny little X, just know that it's there for the X axis, but it could be used for finding both the X and the Y. So what I'm going to do is I'm going to write the kinematic equations the way that I usually write them out when we solve these problems. And then I want you to pause the video, copy it down yourself, and unpause the video, and then we'll go from there. So the important thing about these kinematic equations is that each one of these variables tell us something very specific. So here we have v sub f, so that's the final velocity, and vo, which is the initial velocity, plus a, which is the acceleration, times time. So we have two variables being multiplied by each other. Okay, and so this kinematic equation actually comes from the acceleration formula of vf minus vo over t. And so this formula is just rearranged so that we have vf is equal to the rest of that. Then we have xf is equal to xo, so that's displacement, so you all know, plus v initial times t plus 1/2 a t squared. And we got a little sneak peek of this formula before when we linearize the position versus time graph, right? So for this position time graph, we get a curve shape. So if we linearize it so that it is position versus time squared, you get something that looks linear. Okay, and the important thing here is that if you move this x initial to the other side, you do get displacement. So the displacement is equal to the initial velocity times time plus 1/2 at squared. And the last formula, this actually comes from a topic that we will cover later on, but the topic is called energy. Okay. And within the parentheses there, that is displacement, but the formula sheets will always have that written out. Okay, so here we have these three kinematic formulas, and this is the version that I will be using, but just so you know, on the formula sheet, you will see this version here. Okay, so a couple of other important things as you copy this stuff down. These equations are only used for objects experiencing constant acceleration. So this isn't like, let's say in a car, you're pushing the gas pedal and then you push it more, and then you slam on your brakes and you push the gas pedal. So that is a change of acceleration, so we don't use these equations for that. And the other important thing is when we are looking at free fall problems, or when objects are being dropped, instead of using just a sub y, we would use g for the acceleration due to gravity. And over here, I have a little note about that. Experimentally, the acceleration due to gravity here on Earth should be right around 9.8 meters per second per second. But when we do problems that require us to use a value for g instead of the letter g, we always round it up to 10. Okay, it makes our life a lot easier. All right, so if you haven't paused the video and copied down the formulas, either one works. Please do that now. All right. Now you're back. So we're going to do a couple of problems. So these problems are, I would say this is like a brand new way of solving like quote unquote math problems. So these are problems in variable form only. So we're going to do a total of 3 of these together, but I'm going to give you the strategies that I personally use, and I highly suggest that you use as well when you are solving these problems. So one of the things that you could always do when solving these problems is come up with a sketch. Okay, so a sketch really helps with like understanding the situation, especially if they don't provide a sketch for you. The other thing I highly recommend is when you see a problem like this, one of the things that you should take into consideration is what are your givens, and what are your unknowns. So what I'm going to do is I'm going to read this with you all, and I'm going to highlight all the things that are given, and after I highlight it, I'm going to actually rewrite it all over again. So students are performing a ramp lab. The ball is initially at rest, and this is one of those hidden givens. So if the ball is initially at rest, that means your v initial is 0. It then moves with a constant acceleration a for a time t, and ends with a velocity of v1. The same ball is again initially at rest. It then moves with a constant acceleration of 2a. So this is double the initial acceleration for a time that is a third of the initial time, and ends with a velocity of v2. So the question is, how is v2 related to v1? So this is a proportionality type of problem, and this is the type of problems that you'll most commonly see in our physics course. So now that we've identified all the givens, I'm actually going to create a little table to really help us out. So I know my v initial is, let's see here, my v initial is 0 meters per second. Okay, and my acceleration is just a, and my time is t, and my final velocity is what we call v1. So the way I organize it is that on the left hand side, these are all my variables, and on my right hand side, these are all my givens. Okay, and so I'm just going to draw a line there because now we're looking at a different scenario. Okay, it says the same ball is again initially at rest, so v initial is still going to be 0 meters per second. It then moves with a constant acceleration of 2a, so my acceleration is no longer a, but rather 2a, for a time that is a third of time initial, so my time is actually 1/3 of the initial time of travel, and it ends with a final velocity of v2. So one more time, this left-hand column, these are all my variables, and my right-hand column here, these are all of my givens. Okay, so once you do that, and if you have a sketch, that's fantastic, but I highly recommend that you actually physically write out all the givens that you're given in this fashion. The next thing you have to do is, using the kinematics formulas, you have to identify which one of those 3 formulas gives you everything that you need, as in the like there's no unknown variable here. So what I mean by that is, if you look at the kinematics formulas up here, you'll notice that the top formula has final velocity, initial velocity, acceleration, and time. But the other 2 formulas talk about position, both initial and final. But our problem here does not talk about final or initial position, and we're not trying to find that either. And so because that is our situation, that means we can only use the first formula and not the second and the third. Because if we're looking at the second and the third formula, there's too many unknown variables. Okay, so with that being said, I'm going to go ahead and give you my next piece of advice. And that is, always, always, always start off with your base formula, meaning this is the formula you're going to do your substitutions into. Okay, this is a surefire way of making sure your work is organized. I even like to put like a line underneath of it to like let my brain know, okay, anything above this line is a formula from the formula sheet. And now I'm going to perform my substitutions. So my substitution for v final, according to this table here, is v1, and my initial velocity is 0. Okay, and my acceleration is a, and my time here is t. So I put in the 0 there. So what I'm going to do now is I'm going to clean it up. So v1 is equal to acceleration times time. I'm going to do it again for the second scenario. Okay, and just for the sake of trying to be as organized as possible, I'm going to rewrite the formula, even though I know I'm going to use the same formula. Okay, so v final for this table here, v final is v2 is equal to v initial is still 0, and my acceleration is 2a. Okay, and so I'm here to tell you, parentheses are your friend. Okay, any chance and opportunity you have to show a substitution in parentheses, I highly recommend. It just makes our work a lot cleaner. Okay, 2a, and our time is a third of t. So if I were to clean this math up, I would get 2a times 1/3 t. So I would get 2/3 a times t. All right, so at this point we have V initial, or V1 and V2. So the question is asking, how is V2 related to V1? And here comes your next step. Okay, so to actually solve this problem, what we have to do is we have to create a substitution. And the way that we create a substitution is we look at both V1 and V2 and see what are the similarities that they both share. And in this case, the similarities would be AT. Here is AT. And the reason for that is you want to create a substitution where the substitution is the similarities. So we know that V1 is equal to AT, and AT is the things that they share. So we can substitute that AT, and I'll show you this with my pen. We can put this here, because this is AT, into that AT there. We're going to perform a substitution. All right, and I'll show you that in the line below. So what that would look like here is V2 is equal to 2/3, right? So this is just my original formula, and I'm going to substitute in AT with what we have here. So AT, according to what I just circled, is equal to V1. So the answer would be V2 is equal to 2/3 of V1, right? And then you will look at your answer choices and go from there. And so if the answer choice had everything in terms of V1, you'll say, well, V1 is then just equal to 3/2 V2. Okay, it's just a little bit of algebraic manipulation there. All right, let's try the next one. So here we have a particle that is initially at rest. It experiences a constant acceleration a for a time t and has a final position of x1. The same particle is initially at rest. It experiences a constant acceleration of twice the acceleration for a time of a quarter of the initial t and has a final position of x2. Determine x2 in terms of x1. So we're trying to find that x2 there. All right, so same thing. I'm going to create my table of knowns. We know the particle is initially at rest, so your initial velocity, is equal to 0 meters per second. It experiences a constant acceleration of a for a time of t and has a final position of x1. So xf is equal to x1. Now, this is one of those situations where the problem doesn't give you initial position, and it's one of those things where it's like a known, it's a given, where if they don't give you initial position, we can always assume that the initial position will be just 0. All right? So now we'll look at scenario 2. So scenario 2, our initial velocity is still 0 meters per second. Our acceleration this time is 2a. Okay, and our time is a quarter of the original time, and now we're trying to find, and our final position is now called x2. And once again, because the problem doesn't give us our x initial, we'll just assume that it's 0. And the idea behind that is whenever you measure something, you measure from position 0 and then you measure outwards. Okay, so we have our list of givens. Once again, the left-hand side is a variable and the right-hand side are the givens. Okay, and what we're going to do now is we're going to look at the kinematics equations and see, hey, which one can we use? So I'm going to scroll up, and you should already have the kinematic equations in front of you, but let's take a look. So you have to think to yourself, all right, out of all of these formulas, what has as many of the variables in the problem that is represented in the formula? Okay, and hopefully you figured it out by now, but it is actually the second formula. So the second formula has final position, initial velocity, time, acceleration, and time squared. So what I'm going to do is I'm going to rewrite that formula. Okay, remember, always try to rewrite the formulas in the original base form. So xf is equal to xo plus v initial times time plus 1/2 acceleration times squared. Right? Put a line underneath there because that's my base formula. Final position, x1, initial position, 0, initial velocity, 0 times t, plus 1/2, acceleration is just a, and t is just t squared. Let's clean that up. x1, 0 plus 0t is just 0 is equal to 1/2 a t squared. Okay, so now let's do scenario 2. So scenario 2 would be same thing. Going to start off with my base formula that I'm going to get from my formula sheet. Okay, our final position is called x2. Our initial position is in fact 0. Our initial velocity is in fact 0. Our time is, you know what, I'm going to show this to you correctly, because 0 times anything is 0, but you know, I want to show you my substitutions. So this would be a quarter times t, and because it's a substitution that is gonna look a little bit messy, I'll put that in parentheses just to clean things up, plus 1/2, and my acceleration is 2a, parentheses, and my time is a quarter of the t, and all of that is squared. Okay, so right there, I'm going to take a little note there. This is a common mistake students make. They forget to square the entire value of what time should be. So a lot of times the students just square the t, but you do have to square the quarter as well. So if I were to do the algebra, 0 times everything here is 0, so we end up with 1/2 times 2a times a quarter t squared, and that quarter is also squared, so 1/16 t squared. Okay, I'm going to clean this up even more because I didn't clean it up in the first place, right? So that actually cancels out, and this gives you a 16th t squared is equal to x over 2. Now, I'm leaving the 16th in the denominator, and I don't have anything there in the numerator, but it's important for us to know that in the numerator it's actually a 1. And a lot of the times I find students find it helpful to get the constant, which is 1/16th, and actually bring it out. It helps us to actually see the similarities between the two formulas. Okay, so even though the one that I wrote before in this step, like this is like as condensed as possible, I do find that when solving for formulas, bringing out the constant in the front, it has its uses. So if I compare these two together, I know that they both share at squared. So I want to make that my substitution into here. Right? And so if I do that, I can't just immediately substitute in at squared because I have this 1/2 here. So what I'm going to do is I'm going to make sure that I know what at squared is equal to. So in this case, I'm going to multiply 2 by both sides. I get 2x1 is equal to at squared. So that way I can substitute in this directly into there. So if I were to do that, I will get the following. We will get x2 is equal to a 16th, and my substitution I always like to do in parentheses, at squared is equal to 2x1, and if we clean that up, 2 divided by 16, that gives us an eighth. So x2 is an eighth of the distance of x1. So if you look at your answer and you notice that everything is in terms of x1, we can say that x1 is also equal to x, or 8 times the distance of x2. All right, this leads us to our final problem. This one is in the y-axis. This is something that we haven't done before, and so what I'm going to do is I'm going to read the problem, of course, give you the little tidbits here and there, do the whole highlight anything, and then we're going to try to solve it. Mr. Lee drops a tennis ball initially at rest. Just so you know, this is the first of Mr. Lee's little notes. That's not always given to you. Okay, so when you drop a object, the important thing is that you know that when you first are holding an object and then you release it, okay, after you release it, that's when it moves. But when you're holding it, okay, at that moment, it's not moving at all. And so if the time starts as soon as your fingers let go, okay, for a brief moment of time, the initial velocity is in fact 0. It's not moving in the beginning, okay? For the sake of this problem, I gave you that information, but it won't always be there. From the top of the atrium, that's a height of h. Okay, so that's a highlighted one, and it hits the floor with a velocity of v1. I then repeat the same experiment, but this time I throw the ball down. Ooh, direction matters. A v1, and then hits the floor with v2. How is v2 related to the v1? So I think it's important for this one to sketch it out. We haven't sketched one out before, but this one's going to be important. So normally we say that the bottom or the floor has a position of 0. So y is equal to 0 down here, and which makes that this position up here at the top of the atrium, this is what we're going to call h. So it goes from h to 0. Okay, we have a ball and it's initially at rest, and then it's going to fall, pew, right? And then we have those velocity arrows going down, and it has a final velocity of v1. I'm going to put a negative there, okay, because we know it's going downwards. All right. And then in the next scenario, it's basically the same thing, except now we throw it down. So v initial is actually negative v1. It's going to fall down, pew, right? But this time, it's probably going to be a little bit faster because you threw it this time. Our vf will be negative v2. Okay. All right. So let's come up with our list of tables. Okay. We know that our initial position, our y initial is going to be 0 meters. Our final position, oh, excuse me, our initial position is actually h, not 0. There we go. H, and our final position is 0. Our initial velocity, that's what I was thinking about, will be 0, and our final velocity would be negative v1. And there's a tiny bit of hidden information. We have our acceleration in the y-axis, okay? And our acceleration in the y-axis will always be g downwards, and we represent that downwards with negative. And so if you're thinking to yourself, well, why is it downwards? Well, deceleration due to gravity, it always pulls you down. It always makes things speed up in the downward direction. So that's why it's down. All right, so that for scenario 1. Scenario 2, essentially the same thing, except our initial velocity is, in fact, negative v1. So vf will be negative v2, and our ay is equal to negative g. Okay, so you might have guessed it, but for this one, I would look at the kinematics formula, and it's the one that we haven't used before. So we're going to use that one, and let's see what we can get below. So we have vs squared is equal to v initial squared plus 2a times xf minus xo. So this is my base formula. I'm going to do the initial on the left-hand side. So our final velocity is negative v1 squared is equal to the initial velocity squared, which is just 0, plus 2 times negative g. Our xf is 0, and our our initial height, is negative h. So negative v1 squared just gives us v1 squared. And then here we get 2 times negative g times negative h. So that gives us 2gh. So v1 is in fact equal to the square root of 2gh, or let's see, 2gh to the 1/2 power. Okay, so let's do the same one, but for the final. So for this one, we have negative v2 squared is equal to v initial squared, which is negative v1 squared, plus 2 times negative g, 0 minus h. Negative v2 squared gives us v2 squared. Negative v1 squared gives us v1 squared, plus 2 times negative g times negative h gives us 2g. Okay, and here we can, we'll take a look, right, and we'll try to solve it. So we see here that we actually have a couple of substitutions that we can make. Okay, we can substitute that, and that. I actually didn't have to take it all the way down this far, because if I take a look, I see that this right here has v1 in it, and we solve for v1 right here. So if I perform that substitution, I get, what I mean by that is 2gh, because we want our answers in terms of v2 and v1. So if I substitute in 2gh over here, we get v2 squared is equal to v1 squared, and now time for my substitution for 2gh, which is v1 squared. So that tells us v2 squared is in fact 2 times v initial squared. And we could take the square root of everything, because we want in terms of v2 and v1. So the square root of this and the square root of all of that gives us v2 is equal to root 2 of v1. So v2 is going to be the square root of 2 times bigger than v initial. That's that. I'll see you next time. Bye-bye.